Okay, so we are back. Let's go example 3. So analyze the graph of this polynomial function. And analyze the graph is a kind of specific sequence of steps. You want to find things like intercepts and determine how many turning points there are, things like that. Let's just see exactly what is asked of us. So we observe this is a polynomial. The fact that these numbers, 2.84, 4.2251, and 2.34856, are not whole numbers is okay. As long as the exponents are positive whole numbers, that's what's important for being a polynomial. So this is a polynomial, it's of degree 3. Since the leading coefficient is 1, that's positive. Fundamentally, the end behavior is going to look like x cubed. That's an odd power. So it's down on one side, up on the other. And because the coefficient is positive, it's going to be down on the left, up on the right. What happens in between, we'll find out. So here is the graph using a calculator. Now, what's kind of interesting here is that there's only one root. How would we possibly have found the root of this function? Honestly, you would use a calculator or a computer. Doing this by hand is pretty much impossible. For degree 2 polynomials, you would have ax squared plus bx plus c. How do I find the roots of that? You would use the quadratic formula. If you are of degree 3, is there a formula to find all roots to something like ax cubed plus bx squared plus cx plus d equals 0? There is a formula. It's a nightmare to use. I have never actually used it by hand. I just know it exists. But really, it's very complicated. It's not all that helpful, especially since you could just use a calculator to get a very good approximation. The way the formula works, it's going to give you a very nasty thing involving a bunch of cube roots of things that don't necessarily give you a good idea what the number is. Okay, the y-intercept you can find pretty directly. So remember, the function is down here. The y-intercept is just plug in x equals 0, which means that's 0, that's 0, that's 0. Here's the y-intercept, 2.34856. Okay, so the y-intercept is 2.34856. To find where the root is, yeah, you're going to need to use whatever the respective solving software is on your calculator or software system. A table can give you some points to plot. Okay. They've gone ahead and rounded off to 2 decimal points. That's generally what I would do as well. This is an awkwardly stated problem because these numbers they gave you were not to 2 decimal points, they were to 4 decimal points. So depending on context, you would either round off to 2 by default, because for most purposes that's good enough. But since those numbers already had 4 decimal points, maybe you should round off to 4. The graph tells us that f has 2 turning points. Remember, the graph looked something like this. Here is the one root. It did have 2 turning points. Okay. You can use the maximum function to figure out where this is. You can also use the minimum function to find out where that is. And these are just software. Okay, this is just use the calculator. Can you do it by hand? Yes, this one you actually could do by hand once you have taken calculus. For now, finding these maxes and mins is not something we know how to do other than just ask the calculator to please nicely do it for us. Okay, so if you combine all that information, pardon me, we have things like here is approximately the root, here is the maximum, here is the minimum. Here are some other points that we just happened to compute, and that's just, now we link all these things together. I think it's kind of weird the way the book does this problem, because to find the max and the min, we used a calculator that gave us the graph, and now they're saying use that information to draw the graph. Whatever, I'm not going to ask a question like this, but here it is. Okay, the range is all real numbers. An odd polynomial will always have a range of all real numbers, odd degree polynomial. We can establish where the graph is increasing versus decreasing. Remember, it's just going to be increasing until it hits the maximum, then it's decreasing to the minimum, and then it's increasing from that point forward. So it's increasing all the way up to that maximum, and then from the minimum on. It's also decreasing in between them. Okay, here is a more relevant example. That last one was kind of weird because it was like use a calculator to draw the picture and then get information using the calculator to draw a picture. But here we've got a nice word problem. Here is a chart of data. Based on the number of brochures I sell, here's the cost of printing them. Okay. So can you draw a scatter? Sorry, I should let you pause, copy this down, or just open the book to this example on a separate page, on another tab, or if you have the physical book, all the better. So copy this down. We're going to be referring to this data. Okay. So draw a scatter plot. Comment on the type of relation. That's a very vaguely stated thing. So if we drew the scatter plot, it would look kind of like this. The book is quite confident in stating it's a cubic relationship. I'm going to be honest. I don't think it's that obvious. I'm sure they're going to do a cubic regression and get something that fits really nice and does something like this. However, just based on this small collection of points, there's a linear function that seems to fit pretty well. That's not the worst fit in the world. And in general, if you can fit something with a simpler regression like a line versus a more complicated one, that's usually better. But so using a cubic regression, they've gone ahead and found ax cubed plus bx squared plus cx plus d. Yeah, observe, a is really small, 0.002. B is also pretty small, -0.1. If A is very, very small and B is very, very small, this is very close to just a linear function, cx plus d. So, okay, using cubic regression, we can get this, and then I'll just skip ahead to where it's plotted. Yeah, fine. I guess that looks like it is a better fit than a straight line, but the line wasn't that bad for this range of data, and a line is simpler to work with. In the real world, there's a problem called overfitting. So if I have like a bunch of data points, a line might be kind of good, but then someone else might come in and said, well, I used this advanced regression to give me a degree 97 polynomial that exactly fits this much closer with all of these turning points. And it's like, okay, for the collection of data we were staring at, maybe that's a better fit, but I really don't think that's accurate. It just happens to fit those exact data points better. You used a tremendously complicated function, even though in general, the simpler the function is, the better. And it's called overfitting. Like you used an overkill method to get something that fits extremely, extremely well, but won't actually be useful because it doesn't predict anything other than the exact data points that you were given. This collection of data, while technically a cubic fit looks better, if we go back to the chart of data, it was like, based on how many things I printed, what was the cost? Usually, your cost is going to just be linear. Okay, you print 10 things, they each cost $5, so your total cost was 50. You print 20 things, they cost $5, it's 100. It's just 5 times the number, that's a linear function. So technically you could do a cubic regression here, but if someone came at me with their printing business and said they had a cubic model for their cost, I'd be like, really? But let's go ahead and use that overanalyzed cubic regression to predict the cost of printing 21,000 brochures per month. Well, then you just have to take the function that you've got and plug in 21. Okay, and I just want to point out, again, if we just got rid of these terms, this would not be too far off, okay, because this is so small and this is pretty small. Okay, so sure, it predicts that $17,500 will be the cost of printing 21,000 brochures. Okay, so that's the end of this section. Really, the first video was much more useful, doing a more analytic and thoughtful approach to graphing polynomials based on like their roots and what the multiplicity is. This stuff about using a calculator, it's not as important. And what I did want to get across at the end there is that there is a problem of overanalyzing things. If you just rely on the calculator said this and it was a better fit. So if you take statistics, there's something called an R factor, which tells you how good of a fit it is. Well, your model had an R of 0.98, but mine had 0.999. So mine is better, maybe, but mine was linear and yours had 3 exponentials, a trigonometric function, and an x to the 93rd in it. So maybe you got a slightly better R factor, but I think it was an overfitting issue. So you have to learn how this stuff works in theory rather than just rely on what the calculator tells you. Anyway, that's the end of this section, so we'll keep going with the next one, which is 4.3, I think.